Okay, so now that we've have all these methods to generate 1,2 diols, 1,2 diols can in turn be converted into carbonyl functional groups via oxidative cleavage. So treatment of a diol with per-iodic acid in turn cleaves our diol going through a cyclic periodate intermediate and generates a ketone or carbonyl functionality. So you can use this to generate ketones and aldehydes from diols. So in terms of the mechanism for this process, you can do both the dihydroxylation. So in terms of the mechanism for this process, let's draw out our mechanism for this process. So we have our syn diol. And we treat it with our per-iodic acid. Then we transfer a proton. After our second proton transfer, we now have this cyclic intermediate. We're still just doing essentially bookkeeping to get to the really important step of the mechanism. So after a fair number of proton transfers, we have the following cyclic intermediate. Okay. And in a concerted process, our carbon-carbon bond between our diol is broken, and we generate two ketone functionalities. And just to show, these two carbons with our alcohols become the two carbons containing our carbonyl functionalities. So the periodic acid is serving as our oxidizing agent in this case. Now, another way to generate and oxidize alkenes to generate carbonyl compounds is via ozonolysis. So ozone adds to alkenes to form a malozonide. It's a cyclic intermediate. Now, in general, we don't isolate the products from ozonolysis directly because many of them are explosive. We don't just have the malozonide sitting around in solution. We also have other dioxanes and other higher order oxidized products. The malozonide rearranges under the reaction conditions to yield an ozonide, which can then be reduced with any reducing agent to yield a mixture of ketone and carbonyl functionalities. Now, depending on the workup step and the secondary reagent, which is shown here, added, different ketone functionalities are obtained. So the first and probably one of the more common workups is a reductive workup, where you add a reducing agent such as zinc, acetic acid. Well, this is a pair. So zinc and acetic acid as a pair, dimethyl sulfide, or triphenylphosphine, which is PPH3, to reduce the ozonide, and this gives an aldehyde or a ketone. So in our reductive workup, we generate an aldehyde and product. Alternatively, if we want to generate a carboxylic acid functionality, we can subject this reaction, or subject our ozonide to an oxidative workup. And in an oxidative workup, we add hydrogen peroxide, which oxidizes the aldehyde to a carboxylic acid. So in our oxidative workup, our aldehyde is oxidized and we end up with a carboxylic acid. So it's quite a versatile reaction to generate ketone functionalities from alkenes. So in terms of the mechanism for ozonolysis, so in terms of our mechanism, so let's suppose we start with our generic alkene. Let's now look at ozone. So here is the textbook Lewis structure for ozone. We have addition of ozone to generate our first cyclic intermediate. Okay. And now this ozonide is going to undergo a rearrangement. It's going to undergo a rearrangement to generate our active, to generate the ozonolide species. So as you notice, we first generate the malozonide and then we generate an ozonide. So first and foremost, we kick our electrons down and we generate the following intermediate. Okay, now that we have a now that we have a we have a electrophilic site and a nucleophilic site, let's think about this from the perspective of reactivity. Let's think about this from the perspective of reactivity for a moment. So we have a relatively nucleophilic site adjacent to an electrophilic site, and we have this aldehyde-like functionality. So in our next step, we're going to attack this aldehyde-like functionality. To generate the following potential intermediate. Now we have a nucleophilic site and an electrophilic site, and our nucleophile just attacks our electrophile, and in turn we generate the following intermediate. So this is how we actually generate our ozonolide. Now, suppose we treat it with a reducing agent such as triphenylphosphine. So in this case, when we treat it with a reducing agent, it will attack one of our electrophilic oxygens, and we will generate the following intermediate. So triphenylphosphine is a typical reducing agent, and in our discussion of thermochemistry, triphenylphosphine is a wonderful reducing agent for peroxides and other species because it generates a very strong phosphorus-oxygen bond. Okay, now that we have this, now that we have our relatively nucleophilic oxygen, we're going to kick our lone pair down, and we're going to lose an equivalent of triphenylphosphine oxide. So in the end, after our reductive workup, we generate the following products. So this is the complete mechanism for ozonolysis from the attack all the way to the reductive workup. What I need you to remember is the product distribution when you use a reductive and oxidative workup. And we'll take a look at that actually right now. So we're going to look at two different reactions on two different alkenes with either an oxidative or reductive workup. So in this first case, we treat it with ozone followed by dimethyl sulfide. So dimethyl sulfide, is that an oxidative or reductive workup? Dimethyl sulfide, is that an oxidative or reductive workup? And don't be shy to share your response in the chat. Dimethyl sulfide. So if we go to our list, is that in our list of oxidative or reductive workup reagents? Oxidative or reductive? Reductive. Okay, so we're going to generate aldehyde and ketone products. So we're going to cleave our alkene, and we're going to generate a mixture of a ketone and an aldehyde because we perform this reaction under reductive workup conditions. Okay, let's look at this next example. So we're treating this species, this alkene, with ozone and hydrogen peroxide. Is that an oxidative or reductive workup reagent? Oxidative or reductive? Hydrogen peroxide. Is that an oxidizing or reducing agent? Oxidizing agent. Perfect, perfect. That's exactly right. So in turn, we would expect a ketone, and what functionality results from an oxidative workup? An aldehyde or a carboxylic acid? What do we get out from our oxidative workup? An aldehyde or a carboxylic acid? Yep, a carboxylic acid. Exactly right. There we go. Perfect. So ozonolysis, in terms of product prediction, you don't have to worry too much about stereochemistry or anything of that sort because you're generating sp2 centers. So not too tricky of a reaction. You just had to pay special attention to whether it's performed under oxidative or reductive workup conditions. Okay, let's talk about a relative. Oh, yep. So as you see, by comparison, dimethyl sulfide, which is a reductive workup reagent, yields an aldehyde, while hydrogen peroxide, which is an oxidative workup reagent, yields a carboxylic acid. Let's look at a relative to permanganate oxidation. Let's look at a relative to ozonolysis, which is permanganate oxidation of alkenes. So you can cleave alkenes with potassium permanganate, in which case it generates a carboxylic acid. However, this reaction is not very high yielding. So it's not really talked about a lot in terms of synthetic utility because it's quite a messy reaction. So in our last section, we're going to talk about radical additions to alkenes. And the main reason why we talk about this is even though they don't produce products with very good stereoselectivity, they have very interesting regioselectivity. So the addition occurs to generate the most stable and most substituted radical. The radical then abstracts a hydrogen to place the hydrogen at the most substituted carbon. So as a result of the trends for radical reactivity, we observe anti-Markovnikov regiochemistry. And unfortunately, because we're going through a radical mechanism, the radical addition often results in a mixture of stereoisomers. So in terms of our mechanism here, once we've generated our bromine radical, the radical will add at the carbon so that after addition, we generate our most stable radical. So this tertiary radical is the most stable radical formed from addition. After the radical is generated, then we can abstract a hydrogen to generate our product. And unfortunately, we get a mixture of stereoisomers, but as we can clearly see, we observe anti-Markovnikov regiochemistry. Does that make sense to everyone? Can everyone see how we are observing anti-Markovnikov selectivity, where our bromine ends up, so our bromine ends up on the least substituted carbon. Any questions on this example? Okay, so let's keep going now. In terms of the mechanism follows your typical radical chain process where you have initiation, typically via cleavage of a peroxide, followed by hydrogen abstraction to generate your bromine radical, addition of your bromine radical to generate your most stable radical after addition, followed by abstraction of hydrogen to give the product. Note, we end up with a mixture of stereoisomers, but we observed consistent anti-Markovnikov regiochemistry. Just as a note, in case they throw up or provide a radical addition question, the key signpost for radical addition is the addition of a peroxide reagent. That is your sign that we are dealing with a radical process, and as a result, we need to respect the selectivity for radical addition reactions. Does that make sense to everyone? How the addition of a peroxide reagent changes the mechanistic path from a simple carbocation-based alkene addition to a radical mechanism. Does that make sense to everyone? Okay, so with that, we've wrapped up this chapter. We're now going to switch